Hello everyone, this is our Be Smart in DFT lecture series and here we are with lecture number 3. As promised before, the aim of this lecture series are to make you really smart in your research and to make you so efficient that you can interact knowledgeably with your collaborators. And also, after finishing this lecture series, your package manual will express itself in a much familiar way. Throughout the lecture series, we will try to stick to concepts and some very few easy mathematics. Listen, this lecture will be a kind of travel guide for you through the complicated network of DFT. This video could be a little longer than other videos of this series. That is why I would like to point out the contents of this particular video. In today's tour, at first we will learn about Generalized Gradient Approximation or GGA. Then we will move to Spatially Localized and Spatially Extended Functions. Next, we will take a look at wave function based methods as they play an important role in making hybrid functionals like B3-leaf. And finally, we will see what DFT cannot do. Okay. For the best outcome from this video, sit calm and concentrated. Also, don't lose the flow and complete this video uninterrupted. Okay, in the previous lecture, we had seen that the LDA approximation gives bond lengths and thus the geometries of molecules and solids, typically with an astonishing accuracy of near about 1%. But actually, the LDA is not that good when it comes to the calculation of energies. And it's pretty obvious too, LDA fails in situations where the density undergoes rapid changes, such as in molecules. After the homogeneous density, what people can think of is certainly the gradual change in density with space, or the curvature in density, more precisely, the density gradient. So, in a generalized gradient approximation, the xc functional depends on both the electron density and the gradient of it. To provide you an idea about how much influence this generalized gradient approximation had on the further development of density functional theory, I will just show you the number of citations of two important papers in GGA. First, the paper of Becke. As per today, on 2nd June of 2020, the number of citations of this paper is 47798, really enormous. Next comes the Pardu's paper, number of citations of which is even more, 114658, till the mentioned date before. Truly unimaginable. Now, let's take a closer look on exactly how the gradient of electron density is used. Generally, the most common term that is used in GGA functionals is x sigma equals to mod of gradient of electron density divided by electron density to the power 4 by 3, where the x sigma is a dimensionless quantity and sigma refers to up and down spin state. The formula that Becke used was Ex equals to EXLDA minus beta summation over n sigma to the power 4 by 3 into x sigma squared divided by 1 plus 6 beta x sigma sine hyperbolic inverse x sigma d cube r. This is our equation number 3.3, where this beta is an empirical parameter. Becke worked with the noble gases and estimated the value of beta to be 0.0042 in atomic units. To give you a glimpse of how much improvement GGA gives over LDA, I want to show you the results of Becke. Here are the noble gases and these are the data sheet of exchange energy field in atomic units. At first, we will see the exact exchange energy and then according to LDA, and finally they exchange energy according to GGA. So these are your exact exchange energy according to atomic units. By exact we mean the experimental value. Well, here you have the list of the exchange energy calculated by LDA. And finally, you have the exchange energy according to GGA. As you can see, the exchange energies calculated according to GGA are in pretty good agreement with the exact exchange energies according to the experimental values. Okay, after the exchange energy fit in atomic units, Becke got the beta to be 0.0042. So, as you can see, the results are much more improved in GGA. Beside those type of functionals in which the value of parameter needs to be calculated by fitting experimental data, there are also other types of functionals which are found entirely from the first principles like B86, P, PBE, etc. Other than Becke, some examples of first kind are CAMB, the Cambridge group, PW, FT98, etc. One useful way to classify quantum chemistry calculations is according to the types of functions they use to represent their solutions. Broadly speaking, these methods use either spatially localized functions or spatially extended functions. Here, this is a plot of y1 of x equal to exponential of minus x squared. Then, in red, you have the plot of y2 of x equal to x squared exponential minus x squared by 2. And then here in green, you see the plot of y3 of x equals to 0.1 x squared into 1 minus x whole square e to the power minus x squared by 4. Finally, in black, we have plotted y of x equals to y1 of x plus y2 of x plus y3 of x. A common feature of all these plots is that all of these functions rapidly approach 0 for large values of mod x. Functions like this are entirely appropriate for representing the wave function or electron density of an isolated atom. This example incorporates the idea that we can combine multiple individual functions with different spatial extents, symmetries, and so on to define an overall function. We could include more information in this final function by including more individual functions within its definition. And also, we could build up functions that describe multiple atoms simply by using an appropriate set of localized functions for each individual atom. Spatially localized functions are an extremely useful framework for thinking about the quantum chemistry of isolated molecules, because the wave functions of isolated molecules really do decay to 0 far away from the molecule. But what if we are interested in a bulk material, such as the atoms in solid silicon? We could still use spatially localized functions to describe each atom and add up these functions and describe the overall material. But this is certainly not the only way forward. A useful alternative is to use periodic functions to describe the wave functions or electron densities. Here in red, you see the plot of y1 of x equals to sine square pi x by 4. Then in yellow, you have the plot of y2 of x equals to 1 by 3 cos square pi x by 2. And then here you see the plot of y3 of x equals to 0.1 sine square pi x. And finally, you have the plot of y of x, which is the add up of all these functions. The resulting final function is periodic, that is, y of x plus 4n equal to y of x for any integer n. These are called spatially extended functions, more precisely, spatially periodic functions. This type of function is useful for describing bulk materials, since, at least for defect-free materials, the electron density and the wave function really are spatially periodic. Because spatially localized functions are the natural choice for isolated molecules, the quantum chemistry methods developed within the chemistry community are dominated by methods based on these functions. Conversely, because physicists have historically been more interested in bulk materials than in individual molecules, numerical methods for solving the Schrödinger equation developed in the physics community are dominated by spatially periodic functions. After this classification of the wave functions used to solve the problems we are going to deal with, a second fundamental classification of density functional calculations can be made according to the quantity that is being calculated. In the previous sections, we have emphasized that in DFT the main aim is to compute the electron density, not the electron wave functions. But there are many methods, however, where the object of calculation is to compute the full electron wave function. These methods are called wave function based theory, or WFT. These wave function based methods hold a crucial advantage over DFT calculation in that there is a well-defined hierarchy of methods that, given infinite computer time, can converge to the exact solution of the Schrödinger equation. Suppose we would like to approximate the wave function of n electrons. Let us assume for the moment that the electrons have no effect on each other. If this is true, the Hamiltonian for the electrons may be written as H equals to summation over all individual electrons Hamiltonian, Hi. This is our equation number 3.4. Then the solutions would satisfy H chi equal to E chi. These eigenfunctions are called spin orbitals. For each single electron equation, there are multiple eigenfunctions. So, this defines a set of spin orbitals chi j of xi, where I equals to 1, 2, 3, 4 dot 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 dot. This I represents the position vectors of the electrons with a particular spin state, up or down. From this point, we have shown you the partial glimpse of Hartree theory in the very first lecture of this series, where we have proven the Hartree product, which says that the eigenfunctions of Hamiltonian are products of the one electron spin orbitals. Hence, we can write the wave function of n electrons psi equals to chi j1 of x1 into chi j2 of x2 dot 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 chi jn of xn. This is our equation number 3.6. Unfortunately, the Hartree product does not satisfy all the important criteria for wave functions. Because electrons are fermions, the wave function must change sign if two electrons change places with each other. This is known as the AntiSymmetry Principle. Exchanging two electrons does not change sign of the Hartree product, which is a serious drawback. To save ourselves from this situation, we will take help of Slater determinant. For a two-electron system, the Slater determinant looks like this, where this 1 over root 2 is the normalization factor. Evaluation of the determinant gives 1 over root 2 chi j of x1 chi k of x2 minus chi j of x2 chi k of x1. As you can see, if we put x2 here and x1 here, the evaluated Slater determinant will change its sign. So, this expression has several advantages, like it changes sign if two electrons are exchanged. Then again, it does not distinguish between electrons and It disappears if two electrons have the same coordinates or if two of the one electron wave functions are the same. This means that the Slater determinant satisfies Pauli exclusion principle. For an n-electron system, the Slater determinant is simply a n cross n matrix with normalization factor 1 over root n. Now, in any interesting system, the electrons interact with one another. The many different wave function based approaches to solving the Schrodinger equation differ in how these interactions are approximated. Let's take a look at the approach of HartreeFock method. In this method, the Hamiltonian looks like minus h cut square by twice m grad square plus v plus vh of psi I equal to epsilon I psi I. The third term is the Hartree potential, which has the form Vh equals to E square integration over n by r minus r cap d cube r. Just the term that appeared on cone-sum equation, as you have seen in our previous lecture. In fact, the idea of cone was largely influenced from this paper of Hartree. As you may have guessed already, this equation is also self-consistent. To solve the Schrodinger equation, you need to know the Hartree potential. To know the Hartree potential, you have to have the knowledge of electron density. And to know the electron density, you need to solve the Schrodinger equation. So, here you are caught into an iterative process or self-consistency. To solve the Schrodinger equation in a practical calculation, we define a set of functions that can be added together to approximate the exact spin orbitals. If our finite set of functions is written as phi1 of x, phi2 of x, phi k of x, then we can approximate the spin orbitals as chi j equal to summation over I equals to 1 to k alpha j I phi I of x. When using this expression, we only need to find the expansion coefficients alpha j I for I equals to 1 to k and j equals to 1 to n to fully define all the spin orbitals that are used in the HartreeFock method. The set of functions phi are called the basis set for the calculation. To summarize the HartreeFock method step by step, at first you have to make an initial estimate of the spin orbitals chi j by specifying the expansion coefficients alpha. From the current estimate of the spin orbitals, define the electron density n. Then, in the third step, using the electron density from step 2, solve the single electron equations with spin orbitals. Now in fourth step, if the spin orbitals found in step 3 are consistent with orbitals used in step 2, then these are the solutions to HartreeFock problem. If not, then a new estimate for the spin orbitals must be made and we then return to step 2. Okay, maybe you are thinking like, if we take a larger basis set at the first place, the accuracy of the results will be magnified. True enough, but this will also increase the computational effort needed to solve the equation. Okay, now we will take a look at how do more advanced quantum mechanical approaches make improvements over HartreeFock method. Well, the approaches actually vary over their methodology, but the most common is to include a description of electronic correlation. Electron correlation is often described by mixing into the wave functions in some configurations in which the electrons have been excited or promoted from lower energy to higher energy orbitals. To do this, different groups take hold of different techniques. One group of methods that does this are the single determinant methods, in which a single Slater determinant is used as the reference wave function, and excitations are made from that wave function, which are normally known as post-HartreeFock methods. Another class of methods uses more than one Slater determinant as the reference wave function. Some examples of the first kind are configuration interaction, coupled cluster, molar placed perturbation theory, and the quadratic configuration interaction approach. Each of these methods has multiple variants with names that describe salient features of the methods. For example, CCSD calculations are coupled cluster calculations involving excitations of single electrons. That is why here you have this S, and pair of electrons. That is why you have here D, D for double. While CCSD-T calculations further include excitations of 3 electrons. For triplet, you have an extra T here. Molar placed perturbation theory is based on adding a small perturbation, the correlation potential, to a zeroth order Hamiltonian. In the molar placed perturbation theory approach, a number is used to indicate the order of the perturbation theory. So, MP2 is the second order theory, and so on. For the second kind of method, examples include multi-configurational self-consistent field theory, multi-interference single and double configuration interaction, and n electrons valence state perturbation theory, NEVPT methods, etc. The classification of the wave function based methods has two distinct components, the level of theory and the basis set. For the level of theory, what is seen is how well the electron correlation have been approximated. There is a very popular phrase coined by C.J. Kramer as the longer the acronym, the better the level of the theory. For the basis set, as we have already said, use of more basis set leads to more accurate results. After all this, it's quite natural to look at a comparison. Here, you have a list of computed results with different levels of theory, but with same basis set. We will take a look at a simple molecule, methane. The properties we will look into are CH bond length in angstrom and the ionization energy in electron volt. We will also see the percentage errors compared to the experimental data. And we will also take a look at the relative time taken. The relative time will be calculated according to the HartreeFock method. For the HartreeFock method, our time is 1 unit. Now the different levels of theory will be HartreeFock, DFT, the Bethe functional will be used, MP2 and CCSD. Here you see the CH bond lengths. Then the percentage errors can be seen. Then here you have the ionization energies. All the levels of theory listed in this table predict the CH bond length with accuracy within 1%. One piece of sharing information from this table is that the DFT method predicts this bond length as accurately as the much more computationally expensive CCSD approach. The error in the ionization energy predicted by HartreeFock is substantial, but all three of other methods give better predictions. The higher levels of theory, MP2 and CCSD, give considerably more accurate results for this quantity than DFT. Now, we will take a look at the properties of methane predicted by a set of calculations in which the level of theory is fixed and the size of basis set is varied. In this table also, we will look at the same properties. This table contains results of this kind using DFT calculations with the Bethe functional in each case. For now, you don't have to go much deeper into the detailing of the basis set. Just know that STO3Z is a very common minimal basis set. While in CCPVDZ, D stands for double, in PVTZ, T stands for triple, and then Q stands for quad. In bracket, we have listed the number of basis functions used in each calculation. and also the computational time relative to the most rapid calculation. All of the basis sets listed in this table give CH bond lengths that are within 1% of the experimental value. The ionization energy, however, becomes significantly more accurate as the size of the basis set becomes larger. One other interesting observation from this table is that the results for the two largest basis sets PVTZ and PVQZ are identical. This occurs when the basis sets include enough functions to accurately describe the solution of the Schrodinger equation, and when it occurs, the results are said to be converged with respect to a basis set. When it happens, this is a good thing. An unfortunate fact of nature is that a basis set that is large enough for one level of theory, say DFT, is not necessarily large enough for higher levels of theory. So the results in this table do not imply that the PVTZ basis set used in CCSD calculation were converged. Well, now let me clarify what exactly is B3 functional. See, maybe you are very happy with electron density based theory, but you cannot deny the exactness which wave function methods provide. So, people thought, what if the two theories are mixed and that way a unique class of functionals arose, namely hybrid functionals. Among those hybrid functionals, B3 is the most popular. This is actually by far the most widely used one and the most successful also. Here, B stands for Becke, who worked on the exchange part of the problem. This L stands for Lee, Y for Young, and here P stands for Robert G. Pard, who also wrote a book on density functional theory. Anyway, Lee, Young, and Pard developed the correlation part of the functional, and these three describe the particular way that the results are mixed together, the three parameters used. The exact ratio of this mixture is given by this equation. EXB3 equal to exchange energy of LDA plus 0.20 into exchange energy of HartreeFock minus exchange energy of LDA plus 0.72 into exchange energy of GGA minus exchange energy of LDA plus correlation energy of LDA plus 0.81 into correlation energy of GGA minus correlation energy of LDA. Fine, you don't have to remember this equation, just know that each hybrid functional are a certain ratio mixture of GGA, LDA, HartreeFock and maybe some other method. Fine, after this, it's time for the last part of today's lecture. What DFT cannot do. The first situation where DFT calculations have limited accuracy is in the calculation of electronic excited states. This can be understood in a general way by looking back at the statement of the HK theorems. These theorems only apply to the ground state energy. It is certainly possible to make predictions about excited states from DFT calculations, but it is important to remember that these predictions are not, theoretically speaking, on the same footing as similar predictions made for ground state properties. Another well-known inaccuracy in DFT is the underestimation of calculated band gaps in semiconducting and insulating materials. In some situations, even larger than 1 electron volt error has become inevitable. Third situation, where DFT calculations give inaccurate results, is associated with the weak van der Waals attractions that exist between atoms and molecules. To see that the interactions like this exist, you only have to think about a simple molecule like CH4, methane. Methane becomes a liquid at sufficiently low temperatures and high enough pressures. Whole CNG industry is based on this van der Waal interaction. So this is a pretty significant demerit of DFT. To accurately calculate the strength of these interactions from quantum mechanics, it is necessary to use high-level wave function-based methods that treat electron correlation in a systematic way. Yeah, I know the main question in your mind is which functional I should choose at last. Please wait for some more lectures for the answer because you have to become much more mature in density functional theory to grasp the answer. Okay, a really long lecture, but a much longer thanks to you for your patience. Please subscribe to our channel to get the next video as soon as they are published. Thanks again. Thanks a lot.